Good day, I am Dr. Ohlhoff and I will be discussing Worksheet 9 with you. I have made a sketch of the region D, which is bounded by the curves y equals 0, x equals 1 and y equals 2x. Our first instruction is to explain why the function f has a global maximum and a global minimum on the set D. To do this, we will be using theorem 111. If you can recall, that theorem told us that a continuous function defined on a bounded and a closed region will attain a global maximum and a global minimum on the set D. So we have to check the conditions of theorem 111. The first thing that we have to do is to determine whether f is continuous. Well, f is given as a polynomial function and therefore f is everywhere continuous, hence also on the region D. Next, we have to check that D is a closed and bounded set. Well, D is closed because it contains all of its boundary points. The boundary points are exactly the points here on the x-axis, the points there on that line where x is 1, and the points on this line y equals 2x. Since D contains all of these boundary points, D is a closed set. D is also a bounded set because the x values all lie between 0 and 1 and the y values all lie between 0 and 2. Since we have shown that the function f and the region D meet the requirements of theorem 111, we can now apply the theorem, which says there are points a, b and c, d in D, such that all of the function values of f of points in D lie between f at AB and f at CD. So f attains a global minimum at the point a, b and a global maximum at the point c, d. Our next instruction for this problem is to find the critical points of f. So we calculate the first order partial derivatives of f and find the points where the gradient does not exist. Those are the singular points. In this case, it's clear that the gradient exists for all points in D and therefore there are no singular points. For the critical points, we find the points where the gradient is equal to the 0 vector. This gives us two equations which we've marked A and B. If we subtract equation B from equation A, we can see that y equals x. If we substitute y equals x into A, we get x is a third, and when y is x in B, we get y is a third. At this stage, it looks as if the point a third, a third is a critical point, but it can only be a critical point if the point is in the set D. So let's check that. Well, the x value clearly lies between 0 and 1, so there's no problem. And for the y value, we note that a third lies between 0 and 2/3. Remember, 2/3 is the y value when x is a third. So it follows that our point a third, is indeed in D, and therefore that is the only critical point. Our last instruction for this problem is to find the global maximum and global minimum of f on the set D. This means we have to evaluate the function value at each of the critical points and the singular points, but we know there aren't any singular points, and we also have to investigate the behavior of the function on the boundary. We see that the function value at the critical point a third, is negative a third. Next, let's see what happens on the boundary of D. I've split the boundary into three separate curves, which I've labeled C1, C2, and C3. You can see that on the curve C1, y is equal to 0 and x lies between 0 and 1. If you substitute y equals to 0 in the formula for f, you obtain a function of one variable, namely g at x equals x squared minus x. We now apply our first year knowledge of a function of one variable on a closed interval to find the extreme values for g. you should know that it either happens at the endpoints of the interval or at the critical points. To find the critical points, we need the first derivative of g, which is 2x minus 1. If 2x minus 1 is 0, we get that x is a half, so we know that g possibly attains an extreme at x equals 0, the left point of the interval, or at x equals a half, the critical point, or at x equals 1, which is the right endpoint. Remember that on C1, y is equal 0. So the points that we are really interested in are the points 0, 0, a half, 0, and 1, 0. We calculate the value of the function f at each of these points. Let's see what happens on C2. Here we have x equals 1 and y lies between 0 and 2. And if we substitute x equals 1 into the formula for f, we get a function of one variable only, namely h at y equals y squared. Again, we have to find the critical points. The first derivative is equal to 2y, and that is only 0 when y is 0. So h possibly attains an extreme at y equals 0, the left endpoint, or at y equals 2, the right endpoint. Again, the point of interest to us is the point 1, 2 in D, and we calculate the function value at that point. The point 0, 0 is also of interest to us, but we've already evaluated the function value at 0, 0 in our discussion of the curve C1. Finally, we need to evaluate what happens on C3. On C3, again, x lies between 0 and 1, but y is equal to 2x. If you substitute y equals 2x in the formula for f, you get a function of x, namely p at x, equals 7x squared minus 3x after some simplification. Again, from our first year knowledge, p will have extreme values either at the endpoint of the interval or at the critical points. The derivative of p is 14x minus 3, and if that is 0, we get x is 3 over 14. So h possibly attains an extreme at x equals 0, x equals 3 over 14, or at x equals 1. We have already discussed the function value of f at the two endpoints, so the only new point of interest to us in this case is this point 3 over 14, 6 over 14. Remember, y is equal to 2 times x. We calculate the function value at this point as well. We have now calculated all of the function values at the points where the function potentially can have a local or a maximum extreme. So for the global extremes, we need to find the maximum and the minimum values of this set consisting of those values. As you can see, f attains a global maximum of 4 at the point 1, 2, and a global minimum of negative a third at the point a third, a third. And that concludes our discussion of problem number 1. In problem number 2, we again have a function that is defined by a polynomial, so we know that the function is everywhere continuous, and hence it will also be continuous on this region D that has been described. In terms of the region itself, it's clear that it is a closed and a bounded region, so again we know that by theorem 111, the function f does attain a maximum and a minimum value on D. We also know that to find the global extremes, we need to consider the critical points, the singular points, and the points on the boundary. So let's begin with the critical points. For that, we calculate the first order derivatives of the function so that we can find the gradient. We then look for the points where the gradient equals the 0 vector. As you can see, that turns out to be when x is equal to a half and y is equal to a half. We need to check that the point a half, is indeed in D. For that, we can see that if you look at the x direction, a half lies between 0 and 1, so there is no problem there. In the y direction, you can see that since a quarter is less than a half and half is less than 1, the point a half comma half really lies in D. So we can conclude that the point half comma half is the only critical point of f in D. We calculate the function value at this point and we find that it's equal to a quarter. Next we have to see what happens on the boundary. As you can see, I have divided the boundary into 3 separate curves again, labeled C1, C2 and C3. For C1, y is equal to 1 and x lies between 0 and 1. If you substitute y equals 1 into the formula for the function, you get a new function of one variable, namely g at x equals x squared minus 2x plus 1. Again, you must remember that g can only have extreme values at the endpoints of the interval or at the critical points. We calculate the derivative and find that the only critical point is at x equals 1, which is also an endpoint. Thus, the only points in 0, 1 where g possibly attains an extreme value are at x equals 0 and x equals 1. Therefore, the only points on C1 where f possibly attains an extreme value are the points 0, 1 and 1, 1. On C2, we have x equal to 0 and y lies between 0 and 1. Again, if you substitute x equals 0 into the formula for the function, you get a function of one variable h defined by h at y equals y. We use the first derivative of y to find the critical points, and we know that the other possible points where h can have an extreme value are at the endpoints, and come to the conclusion that the only possible extreme values can be at y equals 0 and y equals 1. Therefore, the only points on C2 where f possibly attains an extreme value are at the points 0, 0 and 0, 1. On C3, we have y equals x squared with x between 0 and 1. Again, if you substitute y equals x squared in the rule for the function, you find a function of only one variable, namely u, with u at x equals, after simplification, 2x squared minus 2x cubed. As before, we use the first derivative of u to find the critical points, and we established that in the interval 0, 1, the only possible points where u can attain an extreme value are at x equals 0, 2/3, or 1. We note that the corresponding y values are for x equals 0, y should be 0. For x equals 2/3, y must be 4/9. Therefore, the only points on C3 where f possibly attains an extreme value are the points 0, 0, 2/3, 4/9, and 1, 1. By considering the function values at all of the points where f can possibly attain an extreme, we see that the global maximum is 1, and that's attained at the point 0, 1, and the global minimum is 0, which is attained at 0, 0 and 1, 1. That concludes our discussion of problem number 2. In the third problem, we are instructed to use the method of Lagrange multipliers to find a solution. As you know, we need two functions for this method. We need a function that needs to be maximized or minimized, subject to a certain constraint, which is the second function. So in this case, if we want to maximize and minimize the value of x plus y, it makes sense to let f at xy be equals to x plus y. The constraint in this case is that the point must lie on the circle with that given equation. So we use that equation to construct the second function, g at x comma y equals x minus 1 in bracket square plus y minus 1 in bracket square minus 1. We cannot simply use a method if we hadn't checked that the conditions are met. The first condition that we have to check is whether the functions are defined on an open set. Well, both of these functions are defined in terms of polynomials. We know that they are everywhere defined, so on the whole of R2, and R2 is an open set. We calculate the first derivatives of these functions, and we see that they are all polynomial functions. Thus, f and g have continuous first-order partial derivatives because they are either constants or polynomials. Finally, we need to check that the gradient of g is unequal to the zero vector for all points on the given circle. So we note that if the gradient is 0, x must be 1 and y must be 1. But the point 1, 1 is not on the given circle, so the gradient of g is indeed not equal to the zero vector for all points on the circle. We may now use theorem 126. So we can define a new function L by putting L at x, y, lambda equal to f at x, y minus lambda times g at x, y. In order to find the critical points of L, we need to calculate the first order partial derivatives of L. You can check the calculations. The critical points of L are where the gradient of L is equal to the zero vector. This gives us the three equations that we've written down there. One of the ways of solving these equations is to multiply the first two equations by x and y respectively. But we need to make sure that we are not multiplying by 0. So note that the point 0, 0 is not on the given circle. Therefore, we may assume that x is not 0 and y is not 0. Therefore, we may multiply the first equation by y and the second equation by x to obtain two new equations named 4 and 5. Since the right-hand sides of equations 4 and 5 are equal, the left-hand sides must also be equal. We can also take out a common factor on each of the left-hand sides, and then we get the equation x times in bracket 1 plus 2 lambda equals y times in brackets 1 plus 2 lambda. And if you simplify that, you will see that you get y is x or lambda is negative a half. If you put y equals x in equation 3, we find that x is 1 plus or minus 1 over the root of 2, and because x is equal to y, that also means y is equal to 1 plus or minus 1 over the root of 2. If we put lambda equals to negative a half in equations 1 and 2, we see that x is 0 and y is 0. But since the point 0, 0 is not on the given circle, we can ignore these values. So the critical points are 1 plus 1 over the root of 2, 1 plus 1 over the root of 2, and 1 minus 1 over the root of 2, 1 minus 1 over the root of 2. Remember, we had y is equal to x. That means the two coordinates must be the same. Finally, we calculate the value of f at these two critical points. We see that in the one instance, the result is 2 plus the root of 2, and in the other instance, the value is 2 minus the root of 2. Thus, the maximum value of x plus y on the given circle is 2 plus the root of 2, and the minimum value is 2 minus the root of 2. That concludes our discussion of problem number 3 and also of this worksheet. Goodbye and good luck.